Hi, welcome back to the course Introduction to Machine Learning in Julia. In the current module on probability and statistics, we earlier learned a little bit about the basics of statistics and a little bit about the basics of probability. But in this particular lecture, we'll be talking about probability distributions. This lecture starts pretty much from scratch. So even if you know nothing about anything that is being covered in this lecture, don't worry, you will still be able to follow through. This lecture is part of our foundation building ML for ML activity. So with each lecture that you finish, you are progressing one step closer to mastering the foundations for machine learning. So welcome to the lecture. So probability distribution is nothing but if you have a bunch of possible outcomes for a random variable, the probability distribution describes how the probabilities are distributed over those possible outcomes. This distribution itself can be discrete or continuous. A discrete distribution can look something like this. So if there are specific countable outcomes as a result of an experiment, then the outcome probability distribution will be discrete. For example, if you are tossing a coin 10 times, then you have different possibilities. You could get 0 tails and all heads. You could get all heads and you could get all tails and 0 heads. You could also get something in between. So the possible number of heads or possible number of tails that you can get are discrete. It can be any number between 0 and 10, and there is a distribution. So that will be discrete. On the other hand, some probability distributions are continuous, or at least can be drawn or considered to be continuous for all practical purposes. And we'll be seeing some of that also today. So the idea behind probability distribution is that if a particular experiment is conducted, there are certain outcomes that are more probable and certain outcomes that are less probable. And probability distribution gives you a basic idea about that. And these distributions are very important in machine learning, especially, which is the whole reason why we are learning that, because distributions model uncertainty in data and they help us make predictions. For example, consider this one called Bernoulli distribution for binary classification. It determines the success or failure of a particular, let's say, a particular experiment. Or it could be true or false for a particular case. So one of the papers that we had recently published on bias in large language models was about the probability for the LLM to make one statement versus its opposite statement. And this was used for studying the cognitive bias in large language models. And whenever we were running those experiments, the outcome of those experiments were essentially these probability mass functions in the form of Bernoulli distributions. Now, probability mass function is a new term that I just introduced. I don't think I have described that or defined that before. So there are two terms that I want you to be aware of. One is probability mass function and another is probability density function. So I'll come to exactly what that means and the rationale behind calling one of them as mass and calling the other one as density. But let's look at these graphs. So here there are two outcomes possible, right? 0 or 1. It's binary. And the probability is here you have some probability for getting 0 and 1 minus whatever that probability is there. That is for 1. So sum of these two will always be 1. So here is the distribution when p equal to 3, p equal to 0.5, here p equal to 0.3, p equal to 0.5 and p equal to 0.7. There are other models called Gaussian distributions. This is very commonly found in nature. So let's say you are considering the possible heights for the student in a class. If the student is, let's say, from India, and if we are looking at male students, the distribution of heights, if there are a large number of students in a class or in a country or in any place, it will look something like this. Most people will have a height close to the average height of that population. Very few number of people will have height which is in the positive extreme, which will be the average plus a positive number. Very few people will have height which are extremely low, which will be on the negative end of the spectrum. And this kind of inverted bell-like structure, actually bell-like curve is called not inverted, it's actually bell shape only. These bell-shaped curves are called Gaussian distributions, which are found very commonly in nature. And we'll be describing this also in today's lecture. Now, let's start with the discrete probability distributions. Here, the possible outcomes for an experiment are countable. So first, let's look at an experiment like something that has a success or a failure. For example, let's say we define success as getting head in a coin toss. Then if somebody gets a head, that success is defined as by the number 1. Failure is defined by the number 0. So if P is the probability for getting a coin to be head, then 1 minus P will be that of the failure. And the value of P will always be between 0 and 1. And the reason why here we are calling this as, so now if we are plotting this graph, right, the graph will look something like this. So this will be on x-axis, we have x equal to 0. This is one of the possible outcomes. X equal to 1 is another possible outcome. X equal to 0 means failure. This could be failure of anything, anything that can be defined in a binary sense. This is a success. So it's not just applicable for coin toss. It's applicable for any experiment where the outcome is binary. And let's say that the P is the probability for success. Then we will plot something like this. This is success. So the height of this will be P, and height of failure will be, this will be 1 minus P. The exact value of P will depend on the particular experiment. Now, why is this called as a probability mass function? The reason why this is called as a mass function is because the values are discrete. If you add up the values on y-axis, here if you add P plus 1 minus P, you get 1. You don't have to integrate and find area under the curve or something like that. Now, you might be wondering, why am I suddenly talking about integration? Because that is exactly what we'll be doing in one of the upcoming concepts called probability density function. So here there is no integration. If you simply add up the values of these y-axis possible outcomes, you are getting a sum of 1. And that's the reason why here it is called as a probability mass function. And this is the formal definition of Bernoulli probability mass function. So P of x equal to the experiment's value outcome equal to small x. If small x equal to 1, meaning if it's success, it's P. If it's failure, x equal to 0, it's 1 minus P. Now imagine you have a biased coin whose probability for getting heads is 0.6. Now heads is in this particular case defined as a success. So P of x equal to 1 is 0.6. The other probability is 0.4. And this is how the probability mass function PMF looks like, what you see in the plot. And if you add the two probabilities, you get 1. And this is used in many other binary classifications also. In machine learning, for example, if you want to classify an email as spam or not spam, you could use something like this. If you want to decide whether in a image there is, let's say it's a scan of a brain, human brain, whether there is tumor or not, it's a binary classification. So this probability mass function, although not used in a formal sense, it is inherent in most of the binary classification problems in machine learning. The second type of discrete probability distribution that I want to talk about is binomial distribution. So binomial distribution, I'm sure you have learned about this in grade 11th and 12th. If you have not heard about this, don't worry, I'll be talking about it right now. So binomial distribution models the number of successes if you perform certain number of trials. Let's say you are conducting n trials, and these trials are also called Bernoulli trials. So each trial has one of the two outcomes. So it could be head and tail. It could be success and failure. It could be some experiment versus whatever is the opposite of that experiment, right? So the reason why here I have written Bernoulli trial is because the outcome of individual trials is binary. However, the number of successes that you will get if you conduct n such independent trials is forming a binomial distribution. So here we have probability for success in each trial, then we have n number of trials. And in the previous case, in the previous Bernoulli distribution, we saw that we were conducting only one trial, right? And the probability for getting head, if you have a biased coin, was 0.6, right? So n was 1 and P of success was 0.6. in this particular case, n will not be 1. In binomial distribution, you are conducting more than one experiments, and the probability mass function follows an equation like this. Now, you might, if you are not comfortable with math, this equation might look very daunting, but this is a very simple equation. So, P of x equal to k, meaning you are conducting n number of experiments, and you are describing the probability to get success k number of times. So if you define success as getting heads, and let's say you are conducting 10 experiments of tossing a coin, and you want to calculate the probability for getting, let's say, 3 heads or 3 successes in your entire set of experiments, that is given by this binomial distribution. And here this equation is fairly simple. So this n and k in the bracket is nothing but nck. Nck is it's like a combinatorials. So it's expanded as n factorial divided by k factorial into n minus k factorial. And n factorial is nothing but n multiplied by n minus 1 multiplied by n minus 2, etc. up to 1. So if it is, let's say, 5c3, then this is nothing but 5 factorial by 3 factorial into 5 minus 3 factorial. And this is equal to 5 into 4 into 3 multiplied by 2 multiplied by 1 divided by 3 multiplied by 2 multiplied by 1. So this is the first, I'm expanding the 3 factorial here, times, this is 2 factorial, so 2 multiplied by 1. So now 3, these two things cancel, 2 and 4, and then this will be 10. So this is 5c3. So, and then this is p raised to k, where p is the probability for getting success in one individual experiment, p raised to k, and k is the number of successes that you are trying to calculate the probability for. 1 minus p is the probability for failure, and power of this is n minus k. Now, this is an example of a binomial distribution. Here you are conducting certain number of coin flips, actually 50 coin flips, right? And here this distribution shows the number of heads, the probability distribution for number of heads in this coin toss. So this is not one coin toss, here n equal to 50. So in this case, can you imagine what is the probability, how many number of heads are you most likely to get? Is it likely that you may get 50 heads out of 50 coin tosses? It's very, very unlikely, because the probability for that is 1 by 2 raised to 50. This is a very small number. So it is very unlikely for you to get 50 heads. It's also very unlikely for you to get 50 tails, because it's on the other extreme. So here on this extreme is all 50 heads. So that's why the graph is almost becoming 0. It's vanishing. Here also it's like 50 tails, because 0 heads means 50 tails. That also is very unlikely. If you are conducting tossing in 50 times, very, very unlikely you will get 50 heads or 50 tails. How about 1 head and 49 tails? That also less likely, very less likely. Opposite case, 1 tail and 49 heads, that also is very unlikely. So by this logic, if you really even logically think about it, you are most likely to get equal number of heads and tails, because each individual experiment is unbiased. So that is the reason why here, if you look at the peak of the graph corresponds to number of heads equal to 25. And as the number of heads increase or decrease, the peak, you are going away from the peak. So this is an example of a Bernoulli binomial distribution. However, here we are assuming that the coin is like an unbiased coin. If the coin has some inherent bias, this distribution can shift somewhat, but the underlying principle remains the same. Now here is a numerical question. Let's say we are tossing a coin 5 times, where probability for getting heads is 0.6 in every single toss. So now we want to find the probability for getting exactly 3 heads in this particular set of experiments. So we know that here n equal to 5, p, which is the probability for getting heads, equal to 0.6, k, which is the number of success events that we would like to get, is 3. And the formula is nothing but, I hate to mention in terms of formula, but that is the easiest way to communicate this. So that's the only reason why I'm talking in terms of formula here. So probability for getting X equal to 3, we are getting 3 successes, number of successes equal to 3 is equal to NCK times P raised to K 1 minus P raised to N minus K, and this is nothing but 5C3 times probability for getting head is 0.6, 0.6 raised to K is 3, 1 minus P is 0.4, 0.4 raised to N minus K is 2, and 5C3 we calculated earlier, this is 10 times 0.6 raised to 3 times 0.4 raised to 2. And the value of that is 0.3456. What this means is the probability for getting exactly 3 heads in a set of 5 experiments, where the probability for getting individually 1 head in every single individual experiment is 0.6, is 34.56%, or in terms of probability, it is 0.3456. This is why the binomial distribution is very useful for us. The next discrete probability distribution that I want to talk about is Poisson distribution. I want to tell you that there are so many different discrete probability distributions out there, but we are only covering the most useful or the most commonly used ones. In machine learning, there are a few more used. I will show you some of those graphs, but mathematically, let's only talk about some finite number of these probability distributions. So in Poisson distribution, what we are trying to see is it tries to model a given number of events occurring in a fixed interval. If you know the average rate. So an example of this is, let's say on an average, you have a shopping mall, you run a shopping mall, and on an average, you get 10 visitors per hour. Now the question is, find find the probability for 30 people to come in 2 hours, let's say. For that, Poisson distribution will help you. I will show you this in a graphical format as well as in a numerical format. But basically, let me talk about the probability mass function here. So here again, the reason why we are calling it as a probability mass function is the outcomes are discrete. You can have 1 person entering, 2 person entering, or 3 people entering, right? In binomial distribution, you could get 1 head, 2 heads, 25 heads, 49 heads, or 50 heads. The outcomes were discrete. Same here in Poisson distribution. So this is the formula where lambda is the average rate, K is the number of successes that we are looking for. That's it, only 2 parameters. E is the normal exponent. So it's lambda raised to K, e to the power of minus lambda divided by K factorial. Now let's take an example, and then after that example, you will have a fairly good idea about this Poisson distribution. So here the question is this, very similar to the shopping mall example. The average number of customers arriving at a store is 3 per hour. So lambda is 3. So this may be based on the data from the last 1 month. So in the last 1 month, maybe you have X number of customers. The total number of hours for which your store was open was Y, and X divided by Y. It's, let's say, 3 customers per hour. Now the question is, what is the probability that of exactly 5 customers arriving in an hour? So this is an interesting question, right? Because although the expected number of customers per hour is 3, it does not mean that 5 customers cannot come in an hour. There is a probability that 5 customers can also come in an hour. So in that case, what would be the probability? So here P of X equal to 5, meaning we are looking at 5 people coming, and lambda is 3 because 3 is the average number of people coming in an hour. And here you can substitute that in the formula and you will finally get a probability of 0.1008. This is roughly 10%. So roughly there is 10% chance that 5 customers can come in an hour. But the question is, for how many number of customers per hour is the probability maximum? In a given hour, is it more likely that 5 customers will come, or is it more likely that 3 customers will come? So here, since the average number or expected number of customers per hour is 3, the probability, if you calculate the probability for P of x equal to 3, let's calculate that. P of x equal to 3 equal to lambda is 3, k is also 3. So 3 raised to 3, e to the minus 3 divided by 3 factorial. And here this is 27 divided by 6. E to the minus 3, which is equal to, I need to use Google, 27 divided by 6 times exponent of minus 3. And this turns out to be 0.2240. So the probability for 3 customers to arrive will be the highest because the average number of customer arrival in that store itself is 3 per hour. Now, the Poisson distribution looks something like this. If lambda equal to 1, if the average value is 1, you can see that this is the number for which there is a peak probability. Actually, let's search, right? We can find the value of k for which this Poisson distribution peaks. So we can do that by differentiation. So p equal to lambda raised to k, e to the minus lambda divided by k factorial. And what we want to find is, for a given lambda, how do you find the value of x for which, or rather, how do you find the value of k for which this value is maximum? So dp by dk equal to 0. So dp by dk is nothing but, so e to the minus lambda is not dependent on k. So e to the minus lambda times dp, or rather d by dk of lambda to the k divided by k factorial. And what I would do is, let me go to Wolfram differentiation derivative calculator. This will be much more easier. So d by dk, actually, yeah, dk of k of lambda to the power k by k factorial. So lambda I will denote by, let's say, L, because that's easier. L to the k divided by k factorial. And outside we have a e to the minus lambda, which is e to the minus L. And this I'll cut and paste here. Okay, I'm not sure if this is going to calculate, but let's see. Math input, online derivative equal to okay, basically what I wanted to find was whether the peak will happen at the point where x equal to lambda itself, meaning if the expected number of people are 3 per hour, will the Poisson distribution, will it peak at 3? That's basically what I wanted to try, but I will not attempt this derivative because this, at least the way it's done by Wolfram, it looks a little bit daunting. So, but anyways, I googled like whether Poisson distribution peaks at lambda, but here it says it occurs at the greatest integer less than lambda, meaning for in this particular graph, lambda is, where is that? Lambda is, let's say, if lambda is 2, the peak happens at 1. So lambda is 2 for this guy, and here it's saying peak happens. I'm not sure if this is true actually. the mode of this is whereas a proposed approximation. Okay, non-integer lambda, the mode is the closest integer that is smaller than lambda. For integer lambda, there are two modes, lambda and lambda minus 1. Okay, probability distribution, and they have given a graph here, for example. So if lambda equal to 1, there are two modes, one is 0 and one is 1 itself. Okay, so there is a peak at lambda equal to x equal to, k equal to lambda itself. Here, lambda is 6, so at 6 and at 5, there are two peaks. Okay, this is fine. I think what I was thinking was, I guess, correct. Just correct me if I'm wrong. But basically, in Poisson distribution, you have peaks where if lambda is an integer, the peak is at lambda and lambda minus 1. K equal to lambda and k equal to lambda minus 1. Anyways, this is interesting. And now let's move on to continuous probability distributions. So in continuous probability distribution, the probability, instead of probability mass function, we have something called probability density function. A simple way to integrate, to kind of make sense of this is, basically mass is what? Mass is equal to integral of density times dv, right? And this can be written as, if density is constant, let's say, or rather density equal to delta mass by delta volume, right? Mass by volume is density, but if you're looking at a small space, a small piece of mass, its density is mass of that divided by volume of that. So similarly, and then here, if you want to get the mass, if you want to get the delta mass, it's rho times delta V. Now, if this rho itself is dependent on the location, let's say, then you have to get, for getting the total mass, you have to integrate rho delta V over, let's say, some position. Let's say position is denoted by R. This rho itself will be dependent on R. So here we can write rho of R. So this is how you have to integrate. So at the end of the day, if you want to get, I don't know why I introduced special R here, because anyway in dv the R is anyway coming. So here you have to integrate to get the mass. Similarly, in probability density function, to get the total probability, you have to perform an integration, which will be area under the curve. We'll come to that. So the first probability density function that I want to talk about is uniform distribution. Obviously, this means that every possible outcome in a range of outcomes are equally likely. So if the range of an outcome of an experiment is between A and B, then any value between A and B are possible. So the probability density function corresponding to this is simply 1 by B minus A. And 1 by B minus A, here B is the maximum value that X can take, the outcome can take. A is the minimum value. And here f of X, the probability density function will be like this. And if you integrate f of X dx from A to B, this will be 1, because the area under the curve is 1. So sum of all probabilities in probability mass function is 1. Area under the curve in probability density function is 1. And how do you get the area under the curve? You perform an integration. How do you calculate this sum of all probabilities? You just simply add them up, right? So this is the logic behind probability density function and probability mass function. The second, probably the most famous distribution, is called normal distribution or Gaussian distribution. The typical Gaussian distribution is symmetric, it is bell-shaped, and it is centered around the mean. So what does that mean? It simply means like this. So if this is a Gaussian, it is symmetric because left side and right side are equal, are like alike. It is centered around the mean. If this is the mean value mu, the center of the peak, the exact center of this is that particular mean value. It is also bell shaped. Why? Because the bell is like this. This is a bell, right? And this looks like a bell shape. This is an inverted bell shape, but this Gaussian is a bell shape. Now the probability distribution function, density function for Gaussian is also very, very famous. And this is the equation for the PDF for Gaussian. Extremely famous. Here mu is the mean, and sigma is the standard deviation. And this equation describes the f of X in the Gaussian as a function of x. So this is x and this is f of x. And normally in a Gaussian distribution, it peaks, this f of x peaks when x equal to mu, because if x equal to mu, this will become exponent of 0, and this will be 1 by square root of sigma, 1 by square root 2 pi sigma. So the higher the value of sigma, the lower the value of the peak, because then the curve will become more flattened, because here sigma or the deviation is much larger, which means the peak will be smaller. So this is the normal distribution. Another thing to note is that in normal distribution, mean equal to median equal to mode. How can we understand that? Why is mean equal to median? Where is mean first of all? Mean is here. So if this is the normal distribution, sorry, pardon my drawing. If this is the normal distribution, mean is here itself, right? This, whatever is the value of x, this is the mean. What is the definition of median? Median is the value that occurs in the center if we arrange the values in a ascending order or descending order. And where is the ascending order or descending order here? This x-axis itself, because this is in the ascending order, the values on x. And which value occurs in the exact middle if this is a symmetric Gaussian? This value, this is the middle value. So that is the reason why mean equal to median. Now what about mode? Mode is nothing but in a distribution, the number that occurs the most frequently. And which is that number? That number is also this, because the peak value is the highest, which means this whatever is this value of x, that is occurring again and again and again for the maximum number of times. So that's the reason why for a normal Gaussian distribution, mean equal to median equal to mode. And the area under the curve, just like any probability density function, it should be 1. Now there are a couple of, or rather 3 things that I want you to note. If you consider one standard deviation away from mean to the left side and to the right side, so this, how do you describe this? Mu plus or minus sigma. Mu is the mean and sigma is the standard deviation. Then it means 68% of the data lies within that. And if you consider mu plus or minus 2 sigma, so this is minus 2 sigma, this is plus 2 sigma, meaning you are going 2 standard deviation away from mean in both directions, then that will capture 95% plus data. Now, if you go mu plus or minus 3 sigma, it captures 99.7% data. You may have heard of 6 sigma methods. Basically, this 3 sigma to the right and 3 sigma to the left is essentially 6 standard deviations total. It covers 99.7% data set. And beyond that, for example, the data over here and the amount of data set over here, they cover only remaining 0.3% data. So most of the data in a Gaussian distribution is found within mu plus or minus 3 sigma. All right. Now, let's think of answering a few of these questions, right? Let's identify the distributions. If something is a single coin toss, what is the distribution? If it's one experiment and single coin toss, it's nothing but Bernoulli. It's a Bernoulli distribution. It is discrete. Number of heads in 10 coin tosses is basically n number of experiments. Basically 10 number of experiments of a single coin toss. So this experiment being a Bernoulli experiment repeated 10 number of times. And the number of heads in that is a binomial distribution. So this is just a refresher. This is binomial distribution. Can you think of if we are trying to count the number of cars arriving at a toll booth in 10 minutes, given the fact that the average number of cars coming every minute is 3, let's say, something like that. Then if we are calculating this is Poisson's distribution, the way this is described. And if we are talking about the heights of students in a class, it's basically Gaussian distribution. So these are the 4 distributions that I have just written here. I have also written a couple of questions. So let's try to answer this. We have a biased coin with probability for heads being 0.7, and this coin is tossed 4 times. The question is, what is the probability of getting exactly 2 heads? So this is nothing but probability for success x occurring 2 times is nothing but number of times experiments are conducted and times nc k is the number of successful outcomes, I mean, number of times you want the successful outcome times p raised to k times 1 minus p raised to n minus k. And what is this? What is n here? 4 times 4c2 times probability for getting success heads is 0.7 raised to k means 2 times 1 minus p is 0.3. 0.3 raised to n minus k is 4 minus 2, which is 2. So what is this? This should be 4c2 is 4 times 3 times 2 factorial divided by 2 factorial into, so this basically n factorial by k factorial into n minus k factorial. So that's also 2 factorial. So this is gone. This is gone. So this is 4 times 3, 12 by 2, 6. So 6 times, okay, this 4c2. This is the answer for 4c2. Not the answer for this entire question, but basically 6 times 0.49 times 0.3 square is 0.09. Whatever is this, that should be the answer for this. Okay. Now, second one is a data set follows normal distribution with mu equal to 100 and sigma equal to 15. What percent of data lies between 85 and 15? So 85 is nothing but mu minus sigma, right? 100 minus 15 is 85. And 115 is mu plus sigma, right? So here the range we are talking about is nothing but mu plus or minus sigma. And we have discussed that 68% of the data falls within this range over here. So the answer is 68%. All right. Now here I'm just showing you the few different distributions that we talked about. A uniform distribution looks like this. This is continuous. So continuous I'll denote by C. This is binomial distribution. Binomial is discrete, which I denote by D. This is Bernoulli distribution. Binomial is nothing but a multiple number of Bernoulli experiments conducted, and you are trying to talk about the number of times a particular successful or certain number of times the successful event can happen. That is what is binomial distribution. Bernoulli is also discrete. D for discrete. Poisson distribution. In the example that we discussed, Poisson distribution was primarily discrete, because here we are trying to count the number of times a particular event can occur in a particular time frame, given the average number of times it occur in a unit time. Then normal distribution is continuous, C. These two we did not discuss in the lecture, but essentially continuous distributions. So there are many more probability distributions that we have not covered in this lecture, but we don't have to cover all of that. Once you get a basic idea about the probability distribution itself and how is it useful, that itself is the purpose of this lecture. So in this lecture, we discussed briefly about probability distributions. We learned that there are discrete distributions and continuous distributions, and we learned a few examples from both of them. We also looked at some numerical examples. So that brings us to the end of this lecture, and I want to appreciate you for following up with this course, because some of the math concepts might be difficult for you, but some of them are fairly simplified. But in any case, you are laying your bricks one by one towards building your strong foundations for machine learning. So I really want to congratulate you for that. So we'll meet again in the next lecture, and thank you so much for following with me in this course, and let's meet soon again. Take care until then. Bye.